So we are looking here at the live calcium K view from my telescope. As you can see, we already have some thin cloud moving in, unfortunately. But we can still see some detail. So if you were here for Boyan's presentation, he would have explained what part of the spectrum calcium K is. So it's a narrow sliver of light down in the near ultraviolet part of the spectrum. If you have young eyes, you could probably see this with your naked eye through the telescope setup I have right now, but my aging eyes cannot. I can't see anything if I tried to view through my telescope right now. So that's why I have a camera installed. And the camera gives us a lot of flexibility in playing with exposure, playing with the gamma. See, I can adjust the gamma here to affect the contrast that we're seeing. You can also play with some things like recording many individual frames from the live video and then using software after the fact to take that series of images and make it into something that is sharper and clearer, sort of like this image here. So this image is captured using the same camera. I've added color after the fact. It was taken as a monochrome image. But I've captured thousands of frames from the video camera and then used software to combine those images, the best of those frames, to make a sharper, clearer image. But we may talk about that a bit more later this afternoon. So I'm going to zoom in again on this bright spot. So if you recall, Simon mentioned that there tends to be a polarity to sunspots. And that polarity can tell us about what solar cycle that spot was created in. And you'll notice that this active region that we see today does have two components to it. So it is possible that this is a part of the sun's surface where a sunspot is starting to be formed, and that there is some polarity. I don't know offhand what it might be, but one of these active regions would have a north designation and the other would be south, just like a magnet. Over time, if we watch these spots, we may find that they tend to get larger in size. They may also start to drift apart, so the space in between might over time get bigger. We'll also notice that the whole thing is moving. I think right now the sun is rotating this way. I'm not sure, but I think that's the direction. So over time, we'll see this change its position, drifting slowly towards the edge. Now it does take a number of days for the sun to rotate, so it'll be moving fairly slowly.
Jim, I've got a couple of questions.
Sure.
Amar is asking, how do we know that the stars more bigger than the sun will be converted into black holes or neutron stars?
It's actually quite well determined by the mass of the star. So when I'm just going to go back out to full screen here to help illustrate. So all of the energy is being produced in the core, which for a star is about the inner 1/4. So that's where all the fusion is happening. Hydrogen is being combined with hydrogen to make helium and other elements. And the energy from that reaction, from that fusion, is pushing out in all directions. And it's only the gravity of the star that is holding it all together. So the gravity of the material outside of the core is pushing it all back down in again. And so there's a balance between those two forces. If the fusion in the core stops, then all of the sun's material will crush down into the center until it reaches a point where some other force takes over to balance it. In the case of our sun, its mass, and scientists know this, that you can do the math on it if you study this sort of thing. But based on our sun's mass, it will collapse down into something called a white dwarf. So the fusion someday will stop. All the mass of the star will collapse until it gets to a point where the force between atoms is enough to keep it from collapsing the rest of the way. So, protons, they don't like being next to other protons in the atom because they have the same charge. So if you try to cram all those atoms together into a small space, they're going to start pushing on each other. And it's that force that eventually stops the star from collapsing. But if you have a star bigger than ours, it's possible that gravity will be stronger than that repulsive force from the atoms, and it will continue to collapse. Into the next stage is called a neutron star, and that's where you've squeezed things so much that all the electrons are shoved into the protons, and they now become neutrons. So all you have left is a soup of neutrons. And those neutrons now have another repulsive force to push themselves apart. And the star stops collapsing there in a neutron star. But if the star is even bigger and has even more mass, it will continue to collapse past neutron star stage to the point where there is no physical force that we know of that will prevent it from collapsing all the way. So all the material from the star will shove into essentially a singularity, a single point. And that is a black hole. So it's all defined by mass and how that mass is balanced with some physical force that we know of in physics that is trying to prevent the star from collapsing.
Thanks, Jim. I got another question.
Sure.
From Daniel, who asks, I'm a solar observer in Montreal, so thanks for answering my numerous questions. Apart from the Charlie Bates solar chat, do you recommend any other solar-themed blogs or internet communities to interact with fellow solar observers?
That's a good question. I think Boyan would be the best one to answer that question.
Yeah. Okay.
I don't know if Boyan is listening still. He might be setting up his telescope. That is a good question. What we can do is when Boyan is back online, we can ask him that question.
Okay, great. I'll take a note and make sure. Another question, this is coming from Keelan. The videos released by the Pentagons were fast-moving this is a little bit off topic. Fast-moving unidentified objects, and the UFO enthusiasts are going crazy over them. Do you have any comments? I don't have any comments. Do you have any comments on that?
I don't have any comments.
No, it's a little bit off topic, so I don't know what to say. If anyone wants to chime in on that one, maybe if they can type some answers or questions through the Q&A.
My only comment on the whole discussion of aliens is, it would be nice if it was true.
It would be nice.
And it's hard to imagine with the number of stars and planets that we have found exist that there isn't intelligent life somewhere. The problem is that things are incredibly far apart in the universe. Like the closest star to ours is on the order of 6 light years, I think, 6 point something. So that means if you were able to travel at the speed of light, it would take you 6 years to get there. And we know that it's not physically possible to travel that fast. Only a photon can travel that fast. So it would take, tens, if not hundreds of thousands of years with the modes of transport that we know of to get to the nearest star, let alone a star that has a planet with intelligent life. So within our understanding of the laws of physics, it's just not possible to get from one system to another system. And it also because of the length of time involved and how long it takes for life to evolve on a planet, it may be that we're out of sync time-wise with another society on a different system. We just have to be out of sync by 1,000 years and we'll have no knowledge of each other's existence. So it's those kinds of realities that make me sort of sadly say, yeah, I doubt it's an alien. Sorry. Anyway.
Thanks, Jim.
I'm going to flip over to the other scope now. So I'm going to stop this share and go back to the hydrogen alpha view. I just need to close the software and start it again.
While you're doing that, Jim, we've got another question. It's a little bit, again, well, sort of off topic, on topic. Dennis is asking, as amateurs, how do you find time to learn and know as much as you do?
Not going to bed punctually, I guess, is when staying up late after the kids are in bed, reading online. Yeah, if you enjoy something enough, then you find time, I guess.
Yeah, I personally am waiting for my retirement in a couple of years, so snatching a couple of hours here and there is sometimes difficult, but it's I keep on saying myself, it's a lifelong hobby. It's not something that you're going to master to any degree soon. And I've only been doing it personally for a couple of years, but my hat's off to people like Jim who have accumulated so much great knowledge and skill. One day might get to a little bit towards their level, but again, it's a lifelong hobby. Anyway, back to you, Jim.
Okay. So here we're back at that prominence again that we looked at earlier this morning. I'm going to increase the exposure a little bit so we can get a better look at it. So I don't know if people remember what it looked like when we looked at it about an hour ago, but it is quite a bit different in shape. It used to be a tidier looking arch, but now it's kind of a combination of a half of an arch and a bit of a curtain. So we would call this here a curtain type because it's just sort of rectangular in shape and it kind of looks like a curtain, I guess. And then this we would call an arch. So curtain and an arch. So this is part of the same structure. So that in this part of the sun, there must be a large magnetic field line that's kind of looping around, that's having an influence on the material. So if we continued to watch this for an hour, it would be even different again. And that's one of the fun things about solar observing, is that it is something that changes on the course of minutes. You never know what you're going to see when you set your telescope up to look at it. And that's especially true using hydrogen alpha. There's so much more to see with this particular wavelength of light. It's unfortunate that the cost of such systems is so high, unfortunately. Now we can take a little stroll around the perimeter, see if there's anything else to look at. I'm just going to jack up the exposure a bit more. There. Now you see, oh, there is a bit of cloud cover. I can see very faint clouds. But let's take a stroll around the perimeter and see if there's anything else to look at here. So there are some smaller prominences. Not too much going on today. Oh yeah, you can see there must be thin clouds passing over already. Oh, there's a little bump there too. So normally there would be always some at least small prominences to see in hydrogen alpha. Now you can also see prominences in calcium K, but they have to be quite bright. So this prominence that we have today, it's not very bright, so we wouldn't be able to see it in calcium K. But if it was really bright, we would. And actually, I have an example that happened. Oh, when was that? So this was from about 3 years ago, I think, in the fall. And I've captured in 4 different wavelengths of light, just because I'm an engineer and I like to overdo it with the technology. So calcium K is the bluish purple image on the left. And you can see what the prominence looked like that day in calcium K. It was a really strong loop feature. I also looked in a green wavelength. The filter is called solar continuum, but it's basically a narrow sliver in the green spectrum that's meant for looking at fine detail in the photosphere. The yellowish orange is hydrogen alpha. It's actually a composite of 2 different exposure times, one to emphasize the prominence and the other to get the detail on the face, on the surface. And then finally, I looked at it in the near infrared. So I used a filter that sees everything above 720 nanometers, which is well into the infrared. And so this is something that I had never seen before. I was quite excited by it. So the prominence was bright enough to be seen not only in calcium K, but also in the infrared band, which I had never even heard of before. So I thought that was pretty exciting. And as I had mentioned, it's fun to be able to record every hour or so, or in this case, I think it was every 15 minutes, and put it together into an animation. And so this is what I was able to put together from that particular day. So these were all individual pictures captured maybe every 15 minutes apart for several hours. And I just tied them all together. Here, I'll loop it here. I use software to put it together into an animation to show actually what is happening with these prominences, how the material is moving around. And it's a little bit misleading because if I render it, if we look over here, can I draw over top? Maybe not. Yeah, I can. Good. There's a loop over there on the left. That material seems to be moving around the loop. And if you clock the speed that it's moving around, it seems like it's moving at incredibly fast speeds too fast to be real, because this loop is larger than the diameter of the Earth. But So material is moving, but it is also changing in temperature. So more of what we see in the loop on the left is that the material in that area of the sun's atmosphere is getting heated by the magnetic field line that's looped around there. And as it heats up, we can see it. When it cools down, we can't see it.
That's a nice segue into another question I have, Jim, from Amar, who asks, could you give a brief description of why the corona, the surface temperature, is more than the internal temperature of the sun?
I was wondering if somebody was going to ask that question. And it just so happens that I have a slide somewhere. Let me see if I can find that. Let me just open up a presentation here. I have a slide to talk around to help explain it. Okay, so you should see a slide here about temperatures on the sun. So here's a cross section of the sun. The inner quarter is the core. The middle 3/4 is, or the middle half, I guess, is called the radiative zone. And then the outer quarter is called the convective zone. And if we look at the temperature in those areas of the sun, this is sort of what we see. So the core is kind of in the 10 million degrees Kelvin range. The radiative zone is kind of 5 to 10 million Kelvin. And then in the convective zone, where all this material is boiling, it's carrying heat out of the inside of the sun very effectively, the actual moving of material.
How do those Kelvin temperatures translate into Celsius, or do they?
It does, yeah. It's just subtract 273 from the Kelvin and you'll get Celsius.
Okay.
Kelvin was set as a unit because it's based on an idea of absolute zero. So if something has 0 degrees Kelvin temperature, it has a very specific meaning to a physicist. It has essentially no kinetic energy. There's nothing moving, no molecular vibration, nothing. So the definition of absolute zero is how the Kelvin scale was set. Then it uses the same sized units as Celsius, basically. So the convective zone brings us out to the part that we see with our eyes, and that's the photosphere at around 6,000 Kelvin. But now if we look outside of that, and this is getting to the question that was posed, what we've been observing today has been in the chromosphere, which is highlighted with the red. So get my tool here. So we were looking at calcium-2, and we're looking at hydrogen alpha. So we're seeing essentially that area of the sun's atmosphere because that's the temperature. The temperature of that material happens to excite calcium or hydrogen in a way that we're able to see it. But as you go further away from the sun, for some strange reason, the temperature goes up. You would think that as you got farther from the sun, the temperature would go down, but that is not the case. The temperature goes up quite a bit. It goes back up to about 1 million degrees Kelvin. And the reason for that is only recently been understood. I'm going to go back to this. So what we can't see in this hydrogen alpha image is that there's lots and lots of loops of magnetic field lines everywhere, all over the sun. And those loops are guiding the material that we can see, but it's also a way for energy to be transferred from the photosphere out into the chromosphere. And another thing that we can't see is in this layer here that we see. I talked about it a bit earlier. There's also a lot of activity in there. There's little hair, if you zoomed in there, that you'd see little hairs called fibrils of hydrogen gas that are like miniature prominences. And that happens all over the entire surface. And these things are moving around vigorously, like on the order of minutes. They're vibrating. And what scientists believe is that the vibration of these fibrils, they basically pluck these magnetic field lines like strings, and they send energy, they transfer energy from the fibril to the magnetic field line, and that magnetic field line vibrates like a string, and so that energy gets transferred up around the loop, and as it's traveling around the loop, it also then transfers that energy out into the outer chromosphere, where it then goes off into the rest of the corona. At least that is one of the main theories of why it's happening. Now, the thing that's a little bit hard to conceive of is the fact that even though the temperature is really high in the corona, I'll switch back to this picture here. Even though the temperature is really high, the density of the material is extremely low. So you could fly your spaceship through the corona, and even though it's at 1,000,000 degrees Kelvin, it is so thin, the density of the material is so low that it would not have any impact on you. Like, it wouldn't transfer enough total energy to you to heat you up because it's so thin, the atmosphere. So I don't know if that helps to answer the question.
So those Star Trek episodes are right.
Yes, except the ones where there's like a big mass ejection and they go right underneath of it.
Yeah.
I don't know if I'd want to do that. Makes for good TV, I guess.